Hi, this is Seyed from EDD Academy, and today I'm going to be covering U-Substitution from Unit 6 on integration. First, what is U-Substitution? So, first let's backtrack and go to the chain rule for derivatives. So, d dx of a composite function f of g of x is equal to df dx times g of x plus f of x times dg dx. Now, an example of this is d dx of x squared plus 2x, all of that cubed. So we take the derivative of the outside, 3 times x squared plus 2x squared, right? And then multiply by the derivative of the inside, 2x plus 2. Now this helps us deal with complex functions that involve composite functions, and that we can identify a clear f of x and a g of x, right? So what do we do for integrals? For example, how do we integrate something that's composite like 2x times sine of x squared dx, right? We have no way of dealing with that. Now, this is where U-substitution comes into play. Like the chain rule, we can use U-substitution to integrate composite functions. Now, how do we do U-substitution? The integral must be in the form of the integral of g prime times f of gx times dx. Now you can probably see this is very similar to the form of the chain rule, right? It's almost like the opposite of it, actually. Alright, we can then set a variable, u is equal to g of x, and du is equal to g prime of x dx, and we'll end up with f of u du. The reason why we do that du is because we need to change the differential as well. We can't do f of u times dx, right? We need to change the entire integral, right? Because in this setting, it's almost like, if you want to think of it in terms of like a graph, right? It's almost like we're transforming the graph a little bit, right? By doing a change of coordinates, right? So if we were changing the length, the height of the rectangle, right? We'll need to change the base of it to compensate. Now, we need an example, all right? So let's go back to the first example we brought up, the integral of 2x times sine of x squared dx. All right, first, look for g of x and its derivative, g prime of x. In this case, we have x squared and 2x. Set u is equal to x squared and du is equal to 2x dx. All right, we have a clear identifiable g of x and its derivative. So by setting g of x is equal to x squared, we can clearly tell that it'll be 2x. We wouldn't choose sine in this situation since there is no cosine to do that. Also, sine itself, we'd have to do sine of x squared, not just sine of x. So we can get that integral into the form of integral of sine of u du, and we know that is going to be minus cosine u plus c because of basic trigonometric derivatives. Now substitute in u is equal to x squared to get the final answer, minus cosine x squared plus c. How about another example? We'll do integral of x squared times e to the x cubed dx. Okay, so we're going to look for a g of x and its derivative g prime of x, just like before. In this case, we could do x to the power of 3 and 3x squared as g of x and g prime of x, respectively. However, if you look closely, we're missing a factor of 3. So how can we do a substitution? We'll see that, x cubed, right? But there's an x squared, but there is no 3x squared. All right, first let's just continue doing the substitution as normal, as if we did have a 3. U is equal to x cubed, and du is equal to 3x squared dx. Now divide the differential by 3 on each side to get u is equal to x cubed, and 1/3 du is equal to x squared dx. This is completely valid because we're just substituting in a constant multiplied by the differential. So it works, right? Because if we do the substitution at the end, it will make sense. We can actually just prove it by taking the derivative of the result at the end. Now to do the substitution, the integral of x squared times e to the x cubed dx will simplify down to the integral of 1/3 times e to the u times du. The next step isn't really necessary since we all know what the integral of e to the u is, but I'll go ahead and do it. We take the 1/3 out of the integral and we get integral of u to e to the u du, and we'll end up with 1/3 e to the u plus c. plug back in the substitution, and then we got u is equal to x cubed, and it'll become 1/3 times e to the x cubed plus c. This is easily verifiable as being the end result, right? So let's take the derivative of it. So we can take the 1/3 out of the derivative, and we'll take the derivative of the outside first, e to the u, we'll say as e to the u, right? And then we'll multiply by the derivative of the inside. So we'll get 3x squared. The 1/3 and the 3 cancel out, giving us x squared times e to the x cubed. So as we can tell, this substitution does work, and dividing by constant will not affect the differential. And this is our final answer. Thank you for watching this short video from EDD Academy. Be on the lookout for our future videos. Hope to see you guys soon. Bye.